Okay, welcome to the people on the YouTube channel. You can hear me now. So for everybody in the stream, keep your mics muted. Unless you want to say something, then by all means go ahead, talk. It's going to be like kind of an interactive session where like if I don't know something, just tell me. Because I am not a very smart man. The list with all the proofs is going to be available in the YouTube description as well as my own channel. And yeah, I think let's just get started. So I have a overleaf thing here, which is just a big fancy LaTeX editor where you can like edit stuff together. So this is where I do all my helpful homework with my brother. So here, this is like helpful homework number 1. Oh, back in the day. Yikes. But I made a little thing for the 20 proofs and I already pasted all of the proofs in here. So I think it's about time to get started with the first one. So we have a proof that the sum of all the I think this is powers of 2 until 2 to the power n is equal to 2 to the power n plus 1 minus 1. Now I know for myself that this is true, because in the binary number this would look like, and that is equal to 0b. So I know that this will hold, but now we have to prove it using the the expected / official proving thing. So when we're working with sums or series or anything infinite or anything non-infinite, we want to get started with with proof by induction. I think that would be the best way here. So let's see. We're gonna say we're gonna use proof by induction. When you see me use these 2 backslashes, that means enter, like a line ending. So because if I do like this, it might not put enter in between them. Yeah, no. So we're gonna use a proof by induction. So let's see. We want to prove this top thing. So first, we're gonna need a base case, and that is that. Or let me first write this down in a little bit more rigorous way. So we can say that this is the sum as let's see. Let's say n is 0 to, or I is 0 to n is equal to 2 to the power of n plus 1 minus 1. Okay, yeah.
Yeah, you forgot the 2 to the power of n in the summation.
Oh, yeah. That might be useful to actually have the thing we're reasoning about in there. So, oh, and now I have an equal sign to little. Okay, so we have, oh, and then this should be 2 to the power of I. Okay, so we have the sum of 2 to the power I as I goes from 0 to n is equal to 2 to the power of n plus 1 minus 1. Yeah, this looks a lot more reasonable, as in that we're better able to reason about it than the other thing, honestly. So, we have the base case, and that is going to be that, and I'm just going to do a bunch of copy pasting here. Let's take n equals 0. By the way, in like a good world, this should give a region. So this should say for n in all the natural numbers, for example. So then this should say, yeah, for n part of natural numbers, this thing will hold. So because it's for all natural numbers, let's start with 1. Or I don't know if 0 is included in the natural numbers. I think that's like up to people to ask. I mean, I'm not sure if zero works as a base case. So in that case, let me just say n is bigger than or n is greater than or equal to. So GEQ greater or equal to 1. So for all n natural numbers that are greater or equal to 1, this will hold. So if we take n is equal to 1, then the sum of I is 0 to n of 2 to the power I is equal to 2 to the power of n. In this case, n is 1, so that's 1 plus 1 minus 1. And if we work that out, we will get so the sum of I from 0 to 1 of 2 to the power I is equal to yeah, okay. So that is equal to 2 to the power of 0 plus 2 to the power of 1, and it is equal to 2 to the power of 2, which is 4 minus 1, and then we get 3 is 3, which holds. So this is our base case proven. Now this doesn't look that pretty. So there's this thing in LaTeX where if you use like $1 sign, it will be just in line like this, and if you use $2 signs, it will be like on its own. But when you use a sum in line, it gets all squished down, and I don't think that looks pretty. So yeah, this holds, and then we're gonna have our inductive case.
Why is the base case not 0?
Because I specify here that n has to be greater or equal to 1.
Okay.
And I think that is because it doesn't hold for 0?
It does, right?
It does hold for 0.
You get 1, and 1 is equal to 2 to the power of 1 minus 1.
Oh, yeah. Oh, you guys are sharp, sick. Okay, in that case I can take this one away, and I can I can replace this with 2 to the power 1 minus 0, 0 to 0, and you get 2 to the power 0 equals to 2 minus, 2 minus 1, which is 1 is 1, which holds. Alright, good call. So, there we have, let me change this real quick, because otherwise it looks messy here. Yeah. So then we have the inductive step, which is that, let me put the things down first, and I'm gonna copy this part over real quick. So basically we're just gonna fill in n and n plus 1 for what is here. So if this holds, then, and again with if then you can use right arrow or the implication sign or whatever you want to call it. This will hold for n plus 1 equals to n plus 1 plus 1. I can of course just say n plus 2, but I'm just gonna write it down like that. So if this holds, or this is the induction hypothesis. No, this is the inductive step. Okay, yeah. Sorry if I'm a little bit all over the place, but I didn't prepare anything for this other than the proofs. Because I want this to be like as genuine and as like first look as possible. I have no clue how to write hypothesis, but that's alright. So if this holds,
it's
then
with an H and an E.
An
H and an E for hypothesis.
an
If you want
A
to
and
know.
then an E?
T
No.
no,
An H, H.
TH. E. No, not I.
Oh, E. Yeah, EI.
Yeah.
Oh, that's like the bane of my existence. So then we can say the inductive hypothesis is that this thing holds, and then we can say
Don't you have to change it to K? Don't you have to make it K, not N?
in which one, the inductive step or the inductive hypothesis?
In the hypothesis.
Yeah, well, I guess I don't think. Yeah, okay. If you were to fill it in, I guess it could matter. So this is
Because then in your inductive step, you want to use K now, right? Because we're taking K
yeah, sure.
to hold.
Let's see. My mind's kind of blanking here. Because I think I'm making a mistake in the thing here.
I just finished this one.
You should say for the arbitrary integer k.
Yeah, yeah.
Yeah,
That's what
yeah,
you meant.
of course. Like for any arbitrary integer k, and I should put that over. Okay, so all right, we're gonna try the thing we're trying to prove. Ah, yeah, okay, I got it back again. The thing we're trying to prove is this. So if we take this and then we have to somehow find the inductive hypothesis in the left side of the equation. So we have this, and then we can actually say, yeah, we can take the n plus 1 out of the sum, because the sum in this case is like 1 plus 2 plus 4 plus is that 6 or 8? 8 plus 2 dot 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 plus 2 to the power n plus 1, or n plus 2 to the power n plus 1. And of course, like I'm not gonna keep this here. It's just like as a quick memo. So we can see this at oops, 2 to the power n plus 1. So we can see this both as the sum of 2 to the power n plus 1, or we can see this as the sum of this thing plus this loose element. So we can split this up into just this to the power n, and then also 2 to the power n plus 1. So let me see if this is properly written. Yeah. Okay. And let me also just change this 1 plus 1 to 2 here real quick. Do you guys understand what I did here? In Dutch we have this thing called zwijgen is toestemmen, so I will take that as a yes. And at any point, if I do something you don't understand yet, just please ask, because I want things to be as clear as possible, and I'm just messing around as well, so it's very well can happen that I make mistakes. But yeah, because of the inductive hypothesis, we know that this thing, the sum of I to n from 2i, is actually equal to this. So that means I can copy this and let's see, this one I can copy this and replace this with this. And then of course you should behind this say by induction hypothesis. Oh yeah, because I'm using the double brackets now, everything takes its own line, so I'm just gonna put it like above the thing. So does this end up making sense? Oh, I think I'm forgetting something. So 2 to the power n plus 1.
I
Plus-
think you're on the right track.
Hmm?
Oh wait. Yeah, I think you're on the right track.
Yeah, no, I think I'm still correct. So let me take away these brackets here. They're unnecessary. And then this should theoretically just be equal. Let's hope it is, because otherwise I'm making a mistake. So we want to end up with 2 to the power of m plus 2. So in that case, 2 to the power of m plus 1. Oh, that's another copy too many. 2 to the power of m plus 1 plus 2 to the power of m plus 1. Oh, yeah. This is equal to 2 times 2 to the power of m plus 1, which is the same as saying, yeah, okay. I didn't see this, but now I do. Same as saying this plus 1, because, you know, it's adding another 2 times. And then you end up with this, which is just on the left side the same as the right side. So in that case, yeah, which holds. So by the inductive theory, I don't know what it's called. So, which holds. So, our proof by induction is complete because we took any arbitrary and greater than 0. I should actually write that down here in the induction text as well. For any arbitrary integer and greater than 0. And then the very, very satisfying thing of putting down a box. Okay. Oh yeah, and there's this thing where it doesn't like to do that, so you have to say greater than instead of like this. So greater than 0. Recompile. Did I mess up somewhere? Whoa. Oh, it seems my greater than is not showing up. Okay, that's why I've got a list of all Oh. It says for some reason you can't just use this. Then why was it showing a box before? SMH my head. Yeah, okay. Fair. Okay. So that is the first proof done. So the second proof. This seems to be an easy one. For all positive integers x and y, if x divides y, then x divides y to the power x. This shouldn't be too hard. So we'll just say take an arbitrary integer. Or actually, yeah, let's do this. X and y. And let's first rewrite some of this. So I'm going to take what we have to prove. And I'm going to rewrite this to a more, like a way that doesn't use the mid thing. So here it says, okay, x divides y, then x divides y to the power x. We can say x, let's see what that is, x. And now I have to think real quick. The left one is the smaller one, so x times k times k, say k1 equals to y, then x times k2 equals to. I always get my things messed up, so I'm just gonna have somebody else check this real quick. Is this correct, like with the visibility?
Yeah, it seems good.
Okay, chill.
Don't they usually use n and m to multiply by a variable, or?
Oh yeah, sure, we can do that too. It doesn't matter what you use to multiply with.
Yeah, I don't know what they'll be hard on the quiz or something.
No, as long as you put down a valid proof, it doesn't matter if you use x, y, epsilon, the capital phi or whatever. As long as it's clear what you mean. Okay, so... Okay. We have x times... So let's see, we have if this holds, then this must hold. So I'm taking this part of the thing, yeah, sure, and I'm putting that down here. Okay, so what we can do now is we can see that y is equal to x times n, as stated here. So we can just literally replace those one on one. Sucks that my clipboard can only hold one thing. I'm going to be copy pasting a lot during this. So this is our y, which we just replaced, and then do that to the power of x. Okay, then we can say x, yeah, okay, so this is x times n to the power of x. So if we take 1 x times n out of that, this will become okay. So in this step, it might seem a little hasty, but we just take one of these x times n's out of these brackets, out of this this power function, and we put it in front of it. And then we can say say n prime is equal to, and then we take this entire second part. Which is integer because n and x are also integers. This is important. If you forget this, they might be like kind of strict on your ass. And then you can say x to the power of m is x to the power n prime, which holds because m and n are some integer. Oh, 2 slashes too much here. And then in the bottom we can still say and therefore, and then the original thing. And then we put a little box thing here. Okay, now to read it through. For all positive integers xy, if x divides y, then x divides y to the power of x. We have to prove this. We can say that that is actually the same as x times n equals to y, and if that is true, then x times m equals to y to the power x. Put this down, we replace it here, take 1 out of the brackets. Yeah, and then we replace this entire part with n prime. Okay, seems good. Next one. At any point, if you have any questions, let me know. As per usual. Assuming you have two positive numbers, a and b, and the equation a squared plus 2a is equal to 4b squared plus 4b holds proof that a equal to 2b. Now, I'm not sure if this is like really that easy, but it seems to be.
It should be.
Yeah. So, okay, take arbitrary a comma b, or I said positive numbers, but I don't think we're going to be doing too much wacky shit, so it doesn't matter if they're numbers or integers. We have we fill. Oh, this dot is in the wrong place. In that gives. Let's see. So that is 2b. Brackets are really important here. Squared plus 2 times 2b is equal to 4b squared plus 4b.
Sorry to interrupt, but aren't you proving the converse here?
Ooh.
Ooh.
Yeah, that's a good one. That is like that is why I was so curious about this one, because it just seems too easy, but let's see.
Yeah, I don't know how else to do it, but
okay, wait, let's see. We take this. And from that, we want to get to a equals to 2b. So, right side, I'm thinking of like a sum of two squares type thing, but it's not a.
yeah, I'm confused as well. I don't know
Yeah,
what to do.
we have to get to the right way without actually using the right thing. Yeah, I don't know. I don't think if it's good enough to just say, fill it in, it holds.
Maybe you can prove the contrapositive? or
Ooh, that's a
something,
good
or-
one because yeah, that's a good one. We want to prove this using the contrapositive. So let's see. So I'll take this thing. Right arrow. Becomes. And then I take this thing. Copy this part. Put it down there. Copy this part. Put it down there. And we're not done yet because that's not a contrapositive. Now we have to use NEQ, which is not equals to. And this is just not equals to. So this is just a standard inequality. Okay. I'm gonna put 2 enters here because otherwise it gets too messy. So this is what we want to prove. Okay, that doesn't seem too hard now. That's a really good point you made. So we have a not equal to 2b. Okay. And I'm gonna put a 1 here for later. So then I can say squaring this gives this is a squared and is not equal to 4. Somebody's ear raping. Please stop. Okay. Then adding 2 times the original equation 1 gives plus 4b plus 2a. Which is what we wanted to get to. Therefore, by proof of contrapositive, using the contrapositive, we have proven that.
Alright, I'm gonna be real. I'm not sure about the adding 2 times the original equation. Whether it is guaranteed that they're still unequal then. Like, how does that imply that they're not equal after you have added the stuff? Because maybe the things were cancelled by each other or something, and then there's
Yeah, you can say that actually. He's right. Because if you have 3 doesn't equal 1, and you would say 1 doesn't equal 3, you can't add both not equals to each other, because then you would say 4 doesn't equal 4.
This is so annoying.
Ooh, this is gets the blood
This
flowing.
isn't true.
Damn it. We were this close.
Who gave up this?
It was somebody who was saying that it came from a. Oh, let me-
Yeah, it was me.
Yeah. Where did you get it from again?
From our this year's Matura finals from extended math. So it was one of the easier questions.
Oh,
I
jeez.
don't know, but they are confusing sometimes. So, but there should actually be several ways to actually solve this. So
Yeah,
think
should be,
creatively.
theoretically. What the fuck is this?
And this is why I like doing these things with you guys, so that I'm not the only one confused.
Should we do a proof by contradiction?
Maybe we
Ooh, that could be. Yeah, because if we say by contradiction that this is not equal, and then we fill it in, and then it is equal, that would be a contradiction.
By contradiction, the first statement holds, but then A does
Yeah.
not equal to B.
That's a good one. I'm gonna leave this up here real quick, and then copy it over, so that we if I messed it up, we can still reclaim it. We will prove this using a proof by contradiction. So let's introduce the claim that A not equal to that. Okay, and now we can just replace all the not equal signs here with equal signs. Okay, and then we can replace this by, but we have stated that these two things were not equal to each other in the beginning of the proof, and therefore this is a contradiction. / therefore yoink paste box. Okay. Let's see. So I can remove this, compile it, and look and check it. So we have two positive things. The equation, if the equation holds, prove that. We want to prove by a contradiction. Let's introduce the claim that this is not equal to each other. We have but we have stated that these two things are not
Isn't
equal to
this
each other.
wrong? Shouldn't be A squared is equal to 4B squared, but then A does not equal to B?
Yeah, I think you're right.
Wait, what did you say?
Oh my god.
Well, the first statement holds. A squared plus 2A is equal to 4B squared plus 4B, but then A does not equal to B.
Oh, so this will be a case of...
Yeah, you're basically saying that the premise is false, but the conclusion is true. It should be the other way around.
Yeah, because... Why is this one so hard? It looks so easy.
It is easy.
Yeah, I'm just bad. Okay.
No, I mean it's really confusing, but I'm not gonna tell you yet how to solve it.
Don't be like this.
Not yet.
I mean, what we can do is like right now I'm going from here to there. So I guess then the thing we have to do is go from there to here, but I'm not sure how to do that.
Maybe we can just skip this one, go to proof 4, and come back to it when we've got a sudden light bulb moment.
Yeah, I'm getting bored of it too. That's a good idea.
I can give you a short tip for that.
I'm first gonna do 4, I think, and then when we get back to it and we still can't figure it out, then I'll take the tip.
Sure.
I was just quickly wondering about proof 2.
Yep.
Yeah. So there's one step that you do like x times n equals x times n, and then something in braces. But like the next step, you say that n prime is x times n. But on the right side, where does the x times n go? Because
so all we're saying in this step over here is that this whole thing, we're just gonna call that n prime. So we just replace that whole thing by n prime, which is an integer.
okay.
And here we have x times some integer is equal to x times some integer, which holds.
Oh wait, fuck! I read it wrong. Okay, never mind.
Okay, sick. Okay. So it says here, for all integers a, b, there are no integers such that a squared minus 9b is equal to 3. So this is a proof in the form of, let's see, so this will be a proof in the form of negative exists No, I don't want to compile my cheat sheet. There doesn't exist an a comma b such that a squared minus 9b equals to 3. So this is the same as saying, because as we know, taking the negative of an exist is equal to for all the negative of this part. So this is the same as saying for all a comma b a to the squared minus 9b is not equal to 3. Oh, and let me put a new line here. Now the question is, which one is easier for us to prove? Oh, and I think, yeah, these are integers, so I think this one would be easiest to prove.
So what I'm seeing here is that you can actually get rid of the b in this question by turning it into a modulus. Because you're actually saying I think that you're saying there is no a squared, such that if you divide it by 9, that you get remainder of 3.
Yeah.
So then you can just, then that makes it a lot easier.
Yeah.
I mean, what I have is also different. I have a different idea, where just like assume this whole statement hold, but then you prove that there is no such integer a and b that makes this statement hold.
Using quadratic formula, or
Yeah, I mean, what I did was just move 9b to the right, and you take the square root. Then you realize the whole thing on the right couldn't be an integer. That's
Oh yeah, that is a good one. I want to try your way. Yeah. Okay. So I'll take out the for all AB because we already have that. So let's just say, I'm still not used to the fact that I have to like add my own enters. So let's try to say, this is equal to. Okay, and then we will take a proof, or we will do a proof by contradiction, namely by stating that for all integers, oh shit, a comma b that this holds. Okay. So then we go here, and we take minus 9b on this side.
It should be plus 9b.
Oh yeah, because you do
Yeah.
plus 9b on both sides. Good call, thank you. Then we take the square root on both sides. So we take square root of this thing is equal to the square root of this thing. Then we take this is equal to just a equal to the square root of 3 plus 9b. Oh, and I have to put some enters. So now we have to prove that for any integer b, 3 plus the square root of 3 plus 9b is not an integer. How do we prove that though?
I have an idea. How I did it was just because you have the 3 plus 9b, factor 3 out, so it will be 3 and 1 plus 3b. So basically you have square root 3 times square root 1 plus 3b. And since square root 1 plus 3b will never contain a square root 3, thus it will be never, the a will never be an integer.
That's a good one. Yeah, I see what you're saying. So you're saying if I do this, then I take the 3 out, and this becomes 1 plus 3b, and that is the same as saying the square root of 3 times the square root of 1 plus 3b, and then we can say since the only way the right side is an integer is when the square root of 1 plus 3b is an contains a square root of 3, or contains or becomes, or let's say becomes
Become a factor, maybe just
a multiple, I think,
yeah.
of square root of 3, but 1 plus 3b will never be a multiple of 3. And therefore this is a contradiction. Therefore, by proof of contradiction, we have proven that yoink. We just need that second thing. So we have proven that there doesn't exist A and B such that, or let's do A and B in this natural number, or the, what is the set of all integers? Non-zero, I think Z.
Yeah, it was.
Yeah, it's it.
Yeah, so we can say there is no A and B element of Z such that A squared minus 9B equals 3.
Nice.
Box. If you want to put a box down yourself, always remember that the B is a capital. Okay.
Could you share this PDF after this?
Oh yeah,
as well?
definitely. I'll put
That'd be
a link to the. I don't know if I can link
you
the
want-
actual overleaf, but I'll at least
Yeah.
put like this and the PDF output.
great.
Do you want to go back to the previous one?
Yeah, sure.
Where
No,
will you
no.
put the PDF?
Yeah,
I will put it both in the the chalkboard channel and in the description of the YouTube video that I'm gonna publish.
Right.
Okay.
Also, no offense, but it's pronounced integer and not integer.
Thank you for correcting me.
Don't want to be an asshole, but
Grammar
future
police
reference.
over here.
so do you want me to send the solution so you can write it using Quatex, because I don't have it?
For proof 3, you mean, or?
Yeah, yeah. It's
Yeah,
quite
sure, go ahead.
Yeah. I'm just going to copy paste it somewhere.
Yeah.
I guess the reasoning and logic channel.
Okay.
Yeah.
Okay. So I'm gonna copy this over here real quick and then make it into LaTeX myself. So it's the proof for question 3. So it says it is a proof. A proof by contradiction, since A doesn't equal B and or equal to B in this case then.
Yeah, in the beginning.
Does not equal. Yeah, does not equal to B. Yeah.
Okay, and this is true. Get both sides for 0. Oh yeah, they do a. Is this like the quadratic formula?
Yep.
Okay. Okay, so let me take this out. Proof by contradiction. So let's introduce the claim that, in this case, this one is true, but let's say then A is not equal to B. Yeah, I see. We were close. So, we know that A does not equal to B and or well, we know that it does, but you know, for the sake of contradiction, a squared plus 2a equals to 4b squared plus 4b. So then we solve for a, or yeah, we'll do that step a little bit later. So we can take this this formula, pull all of this to the right side, equal to 0. And then we actually, copy paste, and then we actually have and this is plus minus this, so quadratic formula with a equals to 1, b equals to 2, c equals to whatever the hell this mess is. So then we turn this
Okay,
in.
do you actually have to type this for
Hmm?
the quadratic formula?
No, I doubt it. I'm just
Yeah,
like,
that's why I just said solve for a.
yeah.
Yeah, okay.
Yeah, no, I you don't have to type this, but I'm just typing it to like be more clear. I think like
Okay.
people will, the people reading it back will appreciate it.
Okay, I see.
So let's see. Then we have the fraction. Alright, this is actually supposed to be in brackets as well. I'll put this in a double thing since it's so big. So we have negative b plus or minus. I don't know if there's a plus or minus in LaTeX. Plus slash pm. So that's negative b plus or minus the square root of b squared minus 4ac over 2a. Oh yeah, and I should put a double closing bracket, one for the square root and one for the fraction. So if we compile this quadratic formula, fill this in. Okay, so then I'll do this one again, and then we have negative b, which is negative 2 plus or minus the square root of 4 minus 4 times 1 times, and then we have c, which is this entire thing. And this is a multiplication. And something to keep in mind if you're using you're using the actual web lab like testing, if you use D like the stars, the asterisks, it's gonna complain and it's gonna turn stuff into italic when you don't want it. So I think they have to use the like dot multiplication thing. I don't know where it is, like C dot. So this one. So then instead of saying types, you'd have to do C dot. But because overleaf doesn't actually think that's bad, I'm just gonna keep it like this because we know what it means. Oh, and then 2a, a is 1, so this becomes 2. Okay. So then I'm gonna copy this over, and it's gonna be 4 minus 4 times. So this becomes 16b squared, and this becomes 16b. And then the negative sign will turn this into a positive sign, and this into a positive sign. So this will become plus 4. Is there a way to like make this?
Yep, it's 4b plus 2 to the power of 2.
Okay, cool. So then we copy this, we turn this into the square root of 4b plus 2 to the power 2. We copy this. I'm doing this like really verbose, by the way, like with a lot of steps, but it's just so that people who don't watch, who haven't watched the video, can actually see what I'm doing here. So I'm gonna take a 2 out of the fraction here. Then I'm gonna get rid of the fraction by turning this into a 1 and this also into a 1. Okay, and therefore we can say that, and this is all like a equals to okay. So now we can say a1 equals to this plus this land, or yeah, no, let's just do a comma. A2 equals to -1 minus 2b plus 1. So that means A1 is equal to 2b, and A2 is minus 2 minus 2b. Okay. A1 poses a contradiction because we said A is not equal to 2b, and A2 is not in the scope of the question because A and B are positive integers. Therefore we have therefore by proof by contradiction we have proven that slash box. My god, is that a box if I've ever seen one.
Nice, easy solution, isn't it?
Easy solution. Like once you see it, it's easy. But like, damn, that was like hard to actually come to.
I don't want to be a dickhead right now, but I will ask you guys: do you want to see an actual easier solution so that you can get all infuriated of how easy it was?
Yeah, sure.
Okay. Take the initial thing you have, like in the first sentence, like a squared plus 2a equals. Now add 1 to both sides.
Fuck off.
I want
You
to
see
die.
that now? You see that now?
Nice.
Anyways, guys, we will now continue on to proof number 5. Add 1 to both sides. Fuck off. Oh my god.
But well, you see that, right? I mean, like
Yeah.
Yeah, now.
Yeah, now we do.
the short multiplication formula. Yeah.
Add
Very good
1 to
job
both
with
sides.
with the.
I was already thinking of like completing the square and stuff, but I thought, nah, that's too hard. Okay, anyway, guys, proof number 5.
Yeah.
Now here we have another thing like the one we just had to prove, where it's like, if really hard thing, then really easy thing. The general consensus for that is,
just add
fuck
one.
that shit, swap it around. Then we're gonna do a proof by contrapositive. Why is my contrapositive wrong? Does it not understand what a contrapositive is? Maybe it, okay.
Lytics is dumb as hell. Or overleaf.
So therefore, we can also say if x is odd, then, or if even, then is odd. Okay. So we can say by our hypothesis. Oh shit. I don't know if it like. Do you guys know? Can you actually call this like a hypothesis, like the first part of this? Because I know you can do it with like the induction hypothesis, but I don't know if you can do it with all hypotheses.
I don't think it would be called hypothesis, would it?
Okay, let's just say by our claim, x is even, so
Why don't you just say by taking the contrapositive?
Yeah, no, I just meant like this part of our contrapositive.
Oh, okay.
So x is 2 times n for some integer n. I'm doing too much Java. I put a semicolon. We will fill that into our into this, which gives. So this is 2 times n to the power squared minus 8 times 2 times n plus 11, which is the same as saying yoink yoink. I'm going to do the same thing again. We read 2 times n, then this thing 2 minus 1. So, or wait. Yeah, I can just say, so this times this. Yeah, okay. For a second I was tripping. I was like, can I do that? And this becomes 16 times n plus 11. And I'll change this into 10 plus 1. You'll see why in a bit. Okay, so when we take this, I can say 2 times n times 2. This will look a little bit janky, but it's alright. 2 times 8 times n. And this is 2 times 5. So everything we have done so far is just logical. It's like just taking the 2 out. So then I can take 2 times this whole thing. And then this one, and then this one. Plus 1. Say n prime is equal to this whole thing. And because is an integer and prime will also be an integer. So then we can say, okay, 2 times n prime plus 1. This is odd, which is what we wanted to prove with our contradiction, and therefore we have proven that yoink paste box. It's really nice to do one of these after you've had one of these. Okay, so that is proof number 5. So proof number 6 is one you guys probably already have seen before. So it's like the sum of all the odd numbers onto 2n plus 1, 2n minus 1 is equal to n squared. So we're working with a sum here. So what's the thing we want to do? Prove by induction. So we want to use a proof by induction. Let's just say like for some n in all the integers. Like for most of these cases, is like this is gonna be mentioned in the exam. But I sometimes forget to write it down. But yeah, this will be provided for you. My recording still running? Yeah. Oh, we're almost an hour in. We're only a fourth of the way there. Let's go. For some and in all natural numbers, this holds. Want to use it proven by induction. So let's take a base case. N is equal to 0. So that means... Ooh. Does it hold? I don't think it holds. Because 2 times 0 minus 1.
I would say maybe just go for positive integer.
Yeah, I was about to say.
Yeah.
Let's just do and or logical and n is greater than or equal to 1. There we go. Base case n equals 1. It's so much fun where you can just change your proof to fit what you want to do. Gives 1 or yeah, just 1 equals to 1 to the power of 2. 1 equals to 1 to the power 2, which holds. Induction hypothesis. I'm just gonna rewrite this again with like the something we did over there. This can be written as the sum of, or a sum with a capital S, of I equals to 0. Is that correct?
I equals to 1 because the start was 1.
Yeah, good call.
No, actually, I think I equals 0 also work because you need 2 times I plus 1. It should be I equals 0. Yeah, sorry.
Yeah, but if we're gonna be summing up, wait,
Or yeah, that's also work. Yeah, I'm thinking about 2n plus 1, 2n minus 1 also work. Yeah.
okay, of the 2n, or this is of. Wait, is this? Okay, so this is I is 1, 2n of 2i minus 1, I think. Is equal to n squared. Let me see if that is correct. Okay, I messed up somewhere. This is a lowercase s10, my bad. There we go. So the sum of I is 1 to n, so when it's 1, the answer is 1, when it's 2, the answer is 3. Yeah, okay, this is correct. Okay. The induction hypothesis is this. Hypothesis is this. Inductive step. Prove that. And then we replace all n's by n plus 1. And we add brackets where necessary. Okay, so we take this. Okay, so again, what I did before with the taking one term out of the thing, so I can change this into the sum of this, and then enter plus with I being n plus 1. Prove that this, okay, and so we fill in n plus 1 here, and we remove that over here, okay. We also know that the sum of this goes to, let's say, by induction hypothesis. We can say that the sum of I from I is 1 to n of 2i minus 1 equals to n squared, so we could just say this is n squared. And let's also take this out of the bracket, so this will become n squared plus 2n plus 1. Okay, and then I will turn this into 2n plus 2 minus 1. And then I will rearrange everything a bit on both sides. This will become n squared plus 2n minus plus 2 minus 1 is same as doing this. And then we have the both on both sides, so we can say which holds, and therefore by proof by our proof by induction is done, and we have proven that. Oh, for this should be for any, of course, because if we want to have for some, then we can just say I is 1. Okay, done. For any n, and then we add a little box. This one took a lot less long than the other ones. That's nice. Ooh, we're starting on our first proof with sets. That's nice. Okay, So we want to prove that the U no the I'm so bad at what these symbols are called.
Union and intersection.
And the what?
This one is union, and the other one is intersection.
Okay, so the
Right.
the union of A and the intersection of A and B is equal to A for any sets A and B. The things, how they're called in LaTeX, are called cup and cap. I find that a lot easier to remember, but unfortunately I'm also going to have to eventually remember this. Okay, so to say the intersection of A and B, and this is probably just going to be a direct proof. So the intersection of A and B is the same as saying all x for which x are in A, and here we use logical and, x is in B. Yeah, so we want to have everything that is both in A and in B. And then the same thing goes for the union. So this is saying every element x in A, or every element, or the element x in A and the element x in B. Oh yeah, I should put backslashes here. So here we have every element that is in A, or every element that is in A and in B. Would this be true though? Because there could be some... Oh wait, no, yeah, because every element...
Yeah, this one is just all elements in A.
Yeah, because if the elements are in A and in B, they're also in A. So, yeah. The question is, how do we...
You can do like distributive law first and then say, okay, x belongs to A or anything else is always... Oh wait.
Yeah, that's what I was thinking, because it's not...
Yeah, never mind, you get the same thing back.
Yeah,
Or
I
you can just...
I thought it was going to be a lot easier.
Yeah,
I mean,
it's probably a very easy
you
step.
can go ahead. No, you can go. You can go. Sorry.
It's probably a very easy step by just saying one thing and assuming that it's x in what A only, but I don't know how it's called.
I think we can just maybe divide into cases, maybe.
Yeah, but there are infinitely many cases because we don't know the universe.
Yeah, I don't think you can divide into cases here.
Oh yeah, true. Never mind.
Technically, you don't need to know the name of the law. You just say, but I think it's distributive or something like that.
Yeah, but let's see. We'll try. We'll try the distributive law.
Yeah, because the right side is.
So.
Yeah, whatever.
Let's see. I have a. Let's see. The distributive law of x or let's say A or Y and B is equal to A or B and A or C. So we'll have. Oh, I already copied it before. So I'll have x in A or x in A and x in A or x in B. Is this correct?
Yeah, but if you simplify that, then you just get the same thing as... Oh wait.
No, we don't.
Wait,
It flips around the
sorry.
signs.
Whoa.
Yeah, this is actually useful. Okay, so if I do this, and then I get... This is same as saying just x in A by the idempotent law. Yeah. So this is all the elements in A and all the elements in A or all the elements in B.
Yeah, but now.
Yeah, what now?
Like
Logically you should be able to deduce that this is correct, but... All the elements that are in A and that are in A or B.
I mean, it makes sense, but I don't know.
Yeah, I don't know if we can just say this.
Let's just
say
take
by
the
impact.
movie.
Just say by
You can
inspection.
just say from the book or something like that.
Yeah, we
If
can
it's
just say
something
by
proven in the book, you don't
intuition.
You just say from the book, this equals to just A, or like all elements in A,
Hmm.
because it was proven in the book.
Yeah.
You don't need to prove it right now.
Yeah. Hmm.
Just say from the book, it follows that this is equal to.
From the book.
I mean, this is
By
what I wrote in the
authority
midterm.
of
This
the
was allowed,
book,
so I think
it
you can
follows that. I don't know if this like genuinely would hold though. Equals to A. Yeah, but all elements that are in A and see, if there is something in B, but not in A, that will be 0. Yeah, that won't be in there. Okay, let me see if we can reason through this with text. For an element.
If you want to simplify it, you could write it in.
What did you say?
If you want to simplify it, you could write it.
Sorry, your voice is really, really, really soft. I can't quite hear you.
Okay, so I was saying that write it.
Can you guys hear him?
No.
But I do think we made a mistake somewhere.
I think this is like, it is true. For an element to be in this set, it has to be in A and A or B. I think this is like, isn't this like...
In the book, the distributive law says A union B intersection and A union A for this is the result.
Hey.
Guys, I have just joined here, but I think what we can do is just say that X is an element of A, is some proposition A, and X is a part of B, is some proposition B, and then we can use the propositional logic to solve it, and then convert back to sets.
Yeah, but like, we already have that, namely, in A is already a proposition here, and we're already in propositional logic.
I guess it's just something that is known. I don't think.
Yeah, I think this might just be like a law.
Yeah, axiom or something like that.
Yeah, I don't know where it would be though.
In the book, that's why you say from
Yeah,
the book it follows.
but isn't there like there should be a name for this? Actually,
I'm not sure. I was trying to
The
find it.
Boolean
right now.
algebra of sets.
Should we just maybe just convert back to the set, maybe? Just from the set, maybe convert back to the site.
yeah, we can try
Yeah,
to.
I do still think there's a mistake in what we did.
This is correct. Everything up on this line is correct. Everything. I just copied the line twice.
No, it's I think correct. I guess.
Let's see, because here we have. Yeah, A or B and C is equal to A or B and A or C. So this is correct.
Yeah.
This is by idempotent law.
Isn't this like substitutive law or something like that?
Distributed.
I think it's
No. That just the conversion, like from the very beginning, like the whole thing. I think it's just some law. I don't remember the name of it.
Let me actually grab the book.
Wait, what was the point of even doing line 2? Why did we have to use the distributive law? Because we just converted it into something that looks pretty much the same.
You mean like from here to here?
Yeah, yeah.
Well, I mean, if we couldn't solve it this way, then maybe we could have solved it this way. But now, I don't know. Let me just grab the book, because I think.
Just say that A intersection B is a subset of A because everything that is an intersection is already in it.
That's what I thought. Maybe we can use the.
And if you use a union of A with a subset of itself, it would just be A again.
Someone just shared something in the reasoning and logic channel, something called the absorption law.
Ah.
Oh yeah.
Yeah. Let me see if I can find it in the thing. So absorb.
It was from a pencast or from a lecture.
I have no clue how to spell absorption.
Oh, I found it in a book, I think. Wait.
Oh, which page?
Yeah, it's page 111 in like the book pages. So 122 in the PDF.
Yeah. 122.
Yeah, it was
Yeah.
on this page. And I
So
didn't
they
find it.
say, yeah, wait, is it the same? Oh no, it's like the. Okay, wait, it's a little bit different.
Yeah, it's not the same, but
Yeah,
I think
yeah.
it's either from a lecture or a pencast.
Okay, it's
Yeah, we
not
can-
the same, but
Yeah, we can use it without proving it.
Yeah. I'm just gonna scroll through real quick, see if it's not anywhere.
Just search it in the PDF.
Yeah, I looked in the PDF for idempotent law, or for what's it called, absorptive,
Yeah, absorption.
whatever the hell. But I couldn't find it. Yeah, no, I don't. I think I know for a fact that it's true, and I know it's probably in the book as well. But
just
yeah.
say absorptive law. Just it exists.
Okay.
I know that. So
We'll just call this by absorption law.
Almost.
Absorption law. Okay. Which is what we wanted to prove.
QED, I hope.
Yeah, QED, I hope. Box question mark. Okay. So we have a
I
question.
think it is the same after like
Would you mind
converted
running? Sorry, go ahead.
Yeah, like page 111, it's like the same after you converted it, like after the distributive law. It is the same, I guess. So yeah, there it says like, but there's no law or something, but they just say it's intuition.
By intuition.
By the intuition hypothesis.
Oh yeah, no, they just make a
Yeah,
truth table. They're like, yeah, no, this is true.
It's true, yeah, by truth table. Okay, yeah, that. Yeah,
Whatever,
can do that.
we'll take the W, or in this case the L, but whatever.
I'm sorry, but could you go through proof 7 again? Because I don't really understand why it works.
Okay, so by proof 7, all we're doing is just logical steps. So in here, the definition of intersection is the elements that are in A and in B. And here we have the definition of union, namely the elements that are in A or the other thing. And then we do the distributive law. Then we do the and then we just say here with the idempotent law. And then in the end by absorption law, which I guess is a thing, that says that elements of A and elements of A or B is equal to A.
Okay, thank you.
And in the book they just make a truth table for this. However, here I am not sure how I think I can do this with this. So in LaTeX you have to escape your. Yeah, okay. So we have a box B, and that is the elements that are in A XOR the elements that are in B. Show that this is equal to A minus B or B minus A. So first of all, do you guys understand what is here?
Yeah, what's that?
Okay, so
Is this
we're
also in the
defining our
book?
own.
Is this also in the book, the box, or?
Yeah, in the book it's a triangle, but I couldn't make a
okay.
triangle.
Oh, okay.
And here they use like the sign for XOR. I don't know if that's like in here. Oh shit. XOR. Oh, I think they use like O plus here or like triangle or whatever. Yeah, I think this is like the official set. The official notation for XOR is the O plus thing. So it will be this. But yeah, this just means XOR, so it's either in one or the other. And we have to show that A XOR, in this case B, is equal to A minus B or B minus A. So...
Time to open Paint. Time to open Paint and make a Venn diagram.
A Venn diagram is not approved, but it is good.
Yeah, it's not
but it is a good
approvable.
way to
Yeah,
have an idea. So that's a real good idea. Thank you. So we're gonna make a circle. Okay, where we're gonna have two circles. This is A and this is B. I didn't say they were pretty. They're just circles. A and B. So in the case of A, X, or B, that would be be this. And let me just image resize or canvas size, put it up here and make the height like 18,000 pixels. So if we have, back to the normal. I make a lot of memes in Paint.net, so I at least know my way around it a bit. Okay. So in this case we have A, X, or B, which would be this, and we have to prove that that is equal to A minus B union B minus A. So that'll be equal to this, to this union this. Logically, we can intuition-wise, we can see that this is true. However, we cannot just put down by intuition. So let's see how. I think I took this question from the book itself, actually. So let me see where I found it. Here. And I can share this on YouTube because this is like just be able to be found online. So here they say, okay, the symmetric difference of A and B, if A x part of A, x or x part of B. Yeah, okay. I thought I would give like a clearer definition, but it doesn't. So let's first convert this stuff to what's it called? Like predicate logic in a way.
Position, yeah.
Yeah. So we're gonna take this, and this is equal to. Oh shit, wrong one. The element. Oh, this is one too many. The element that are in A and not the elements that are in B, or the element that are in B and not the element in A. So what we have here is, oh god, that looks horrendous. Oh yeah, the not should be before the in. Yeah, so we have x part of A or x part of B, and x not part of B, or, and that should be the logical next step, so this should be a logical or. And we can say this by definition of the union. Okay, so now we have it in this type of statement. However, now we have, if we look for exclusive or, let's see, how does it define this? I want to see for like a more like proper definition of XOR.
You can write it as not if and only if.
Yeah, it's like because I remember if and only if is the same as XNOR, so I know it's like the opposite of that. But I like this is because I know by definition that XOR can be written down as A and not B or B and not A. But I'm not sure if they give that definition in the book.
You can, you know, we know what is the definition of if and only if, and I think that's assumed that on the exam we can use that. So then we can.
Yeah, that's true. Like, I know I could theoretically just say this is the same as that. However, we will probably not be allowed to do that on the exam because we don't have that definition of XOR. Like here, if I say, if I go to Google XOR definition, exclusive or on Wikipedia, it will say it can be expressed in A and not B or B and not A, which is the way we have it here. However, we're not allowed to use this definition, so we're going to have to do a little bit more work. So I'm going to copy this, and by the way, because this is predicate logic, you can actually view this X in A as some kind of predicate, like say in A or whatever. So we can use all laws of predicate logic in this world as well. I know I could probably use the distributive law here, but that would be a hell of a lot of work.
What if you look at the XOR truth table and take the DNF, because the DNF is exactly the same thing you got.
Yeah, that is true.
And basically you can say by DNF, this is
by
the same
DNF. Yeah, I guess that. I guess we could make a truth table.
Like the XOR truth table, and you can say, you can take the DNF, and the DNF is the same thing as the one with the sets.
Yeah, we can try that. So I'm gonna yoink a truth table from here, because I still have some truth tables lying around. So we can say we take the truth table of, let's see, we have A and B. We need only half as many rows, and we have, we'll take just one is enough. So we say X in A. Can I not use math within this? X in B. Oh, I think you can already like automatically use math. Okay. And then we have n xo plus, or x in A o plus x in B. That's actually quite a good exercise because now we can like see how truth tables work like this. Oh, and here I have way too many cells, so this should be only 3. Making truth tables in LaTeX, probably not the best idea on your exam, but they're probably not going to ask you to. And if they are, they're going to give you like an easier format. So 0, 1, 0, 1, 0, 0, 1, 1. An exclusive OR is this. Okay. If we take the DNF of this, we can see that this thing, and put this into the big ass math signs, is equal to this thing wait, can we say that? Yeah, because like not like 0 here is the same as saying not equal. I guess we can add like one more little step here, saying that instead of not x in B, we can say neg x in B. And the same here, instead of saying x not in A, we can say neg x in A. In that way we can like see the more predicates, because here we have like x in A and not x in B, or x in B and not x in A. So disjunction of conjunction. Yeah, okay, so this is correct. And then I can just copy this over to here. Which is what we had, and therefore and then we add a little box. Okay. I thought that proof was gonna take a little longer. That's sick. Okay, so we're at 8 proofs out of 8 proofs out of 20. Let's see. Yeah, some of them are really easy, some of them are really hard. Looking at you. Okay, so let's see. Proof 9 is for all n greater than or equal to 1 that are natural numbers. And here you can see this is like the way it should have been written down. We can say that the sum of n is from the sum. Actually, let me change this into a double math sign so it looks a little bit more readable. The sum of from I goes from 1 to n of I times I plus 1 is equal to n times n plus 1 times n plus 2 over 3. Boy wee, this sure looks like a lot of fun. So we're going to use a proof by induction here. I think that would be easiest. Yeah, that would be easiest. So we will use a proof by induction. Take our arbitrary integer. Oh wait, this is a little too early. Say base case n equals to 1 gives 1 times 1 plus 1. Let me put some math numbers around this. Is equal to the fraction of 1 times 1 plus 1 times 1 plus 2 over 3. Then I'll put an intersign. So here we can say 1 times 2, that's just 2, is equal to 1 times 2 times 3, which is 6 over 3, which equals to 2. Therefore the base case holds. Take arbitrary integer n. Okay, still not, we're still not there. Induction hypothesis, and that is that for all just this whole thing, inductive step. Oh, let me put some more backslashes. You can never have too many backslashes. Okay, take an arbitrary inductive step. So we want to prove that, and when we copy this, oh, this is gonna be a fun one. Oh, so this is gonna be equal to n plus 1 of this stuff, and then this is gonna be n plus 1, n plus 2, n plus 3 over 3. Boy, this sure looks fun. Yep. Okay. So we say take arbitrary integer. Wait. Say we want to prove that this. Take our for an arbitrary integer n, because I know people are gonna be bugged by that. Okay. Or n greater than or equal to 1. Okay, so we're gonna do the thing again where we take out one of the elements. Let me check real quick. Yeah. So we're gonna do the thing where we take out one of the elements, which is gonna be in this case n plus 1 times n plus 1 plus 1 plus, and this just becomes n. Yeah, because we fill in n plus 1 here. And that is equal to this thing. Okay. And now we can say by the induction hypothesis, and then we take this thing, but instead of the sum here, we can say this is equal to the fraction of this thing. So now we're only working with fractions. Boy, this sure looks like a lot of fun. Oh no.
Multiply by 3.
Yeah, that's true. It's probably best if we multiply everything by 3. So then we copy this. I'll do 3 times this. I'll take away this fraction here. And I'll take away this fraction here. I'll take away this fraction here, and I'll take away this fraction over here. Recompile. How does that look?
You
A
can
little bit
divide-
better already?
You can divide by n plus 1.
Yeah, I was about to say, since... can we
Yeah,
do
from
that?
here?
Yeah, n cannot be...
Actually, from here you already kind of done it because there are two
yeah,
common factors.
like
on
I can
that
say
side.
n plus 1 is equal to this whole thing. So then if we divide both sides by... Oh, shit. We divide both sides by n plus 1, we get
But
this.
also,
Hmm?
n plus 1 plus 1 is n plus 2, so you're really close.
Yeah. So we have 3 times n plus 2 plus n plus... n plus 2 is n plus 2 times n plus 3. So,
Wait, but you have to prove that this is correct. So why are you having equal signs?
Hmm?
You should take the left hand side.
Yeah.
Work on it, so to get the right hand side. But you shouldn't have like an equal sign between them.
Yeah. Yeah, okay, I guess. That's no
Yeah.
problem. That means, like,
Yeah.
I can just add, like, n plus 1 times this whole thing. And then I'll just keep, like, the n plus 1 here. I mean, Yeah, okay. Because,
You
like,
also have-
otherwise we have to, like, build it back on, which we don't want to do. Yeah, that makes
you
sense.
also have like equal sign with a question mark on top of it. Don't know what it's called.
Yeah, that
but,
would work too. But there is no reason to write it on each line.
Yeah, I'll just, like, keep doing like this. And that means that... Let's see... To include this part in our thing, I have to do fraction of this thing divided by 3 is equal to this fraction alright, which is equal to the fraction of this thing plus this thing over 3. I would not want to be the one who has to check this. Let me see. Wait, is it actually compiled already? Yeah, I was about to say. So we want to have this whole thing equal to that thing. I'll take away these 2 lines. Okay. So that means I can factor out the n plus 1 here, like I did before. And that is equal to this whole thing. Yeah. And then we have 3 times n plus 1 plus n plus 2 plus n plus this thing. I'll actually do that up here already, because then I can say this is 3 times n plus 6 plus n squared plus 2n. I think this is still correct. Yeah, I think so. And then we can... Yeah, and then we have n squared plus 5n plus 6. Which, by like making a table, you can easily see that that is equal to n plus 1 times n plus 2. N plus 2, n plus 3. Or n plus 2, n plus 3, yeah. Which holds so by the... so that concludes our proof by induction, and we have proven that. Yoink. And then we add a little box. Wow, this does not look pretty, but I think this is okay, cool. Proof 10. Ah, yeah, okay, so we're gonna have our first recursively defined set proof. So we recursively define the set S, say 0, 0 is part of S, if, and I'm gonna have to say, in every single proof, there needs to be another line, or with every single definition of a set, there needs to be another line saying there is no other element in S, which is not there. But that's because I wanted to keep the line short. I'll add it up right here. It looks like Christmas stuff with all the red and green. Anyways. There are no other elements in S. Prove that if m, n is in S, then 5 divides m plus n. We will recursion. We will use, what's that called again? Like
induction?
Yeah, no, like induction over a set, over like structural induction. Structural induction. Base case 0, 0 is in S. 0, 0, or let's say 5 mid 0, because 5 times 0 is 0, which holds. Induction hypothesis. If this divides, if this is an n, then that divides m. If this is an f, then that divides, then 5 divides that. How do we properly say this? Do we say like this right arrow and in this case it wouldn't be n plus 2, but it wouldn't be m plus 1, but it would be m plus 2 and m plus 3? Is this a proper way to say this though? Let's quickly open the book and see, look how they do structural induction. Oh, structural induction.
I think you have to, in the base case, you should prove like all the recursive definitions. I think in the base, basis, so which is the base step or base case, you should prove all the recursive definitions. So to 0, 0, you should add 2 and 3 and show that it's still divisible by 5.
I think that's actually what they do here in the inductive case.
Yep.
Okay. We want to show that if statement is true for prop, then it is true for Yeah, and this here has like 2 different.
Yeah, maybe take the
steps.
previous one. I think there is one before that, because the one with prop is a bit.
Yeah,
strange.
sure. Yeah, okay. Prove that P holds. Prove that for every element in the set, if P of K, then P of K plus 1.
Yeah.
Yeah, okay. We'll take that notation. That's good. So we can say for all elements this in S, if this holds, then and then 5 divide. Let me see. Did I have the correct amount of brackets everywhere? Another one too many over here. One, and that's like properly over there. Oh, I forgot the 5 here. Wait, so this is the inductive. This is the inductive step, and the induction hypothesis is this one. Okay. This is good, because this is like the first time I've written this structural induction, so it's a good training. So we can say, okay, the base case 0 and 0 is an S, 5 divides 0, which holds. The inductive hypothesis is if this is an S, then that, and we can say here, for the inductive step, that 5 divides, for all M and N, part of S, 5 divides, if 5 divides this, then 5 divides that. Okay. So then we go on and say so we know 5 divides this. So let's have a look at the right side. So we want to prove that to prove this thing for any M N in S. This thing holds. Okay. So, oh, there's a bunch of spaces in front of here. Oh. I know people are going to be mad at me if I don't take this away. Okay, to prove, so we have to prove this. So then we say 5 divided this actually means that 5 times. Yeah, they're already using x and m, so we're going to use x, m and n, so we're going to use x and y, which can be rewritten to if this is in. Okay. Oh, shit. Oh, I forgot to copy over this. Then 5 times y is equal to m plus n. Okay. A few more spaces. Let me add like another new line between every step to keep it a little bit more clear, because it's a bunch of text now. And let me put some brackets around here. Okay, so if m and n are in S, then m plus n is equal to 5 times y. Okay, so then we can rewrite this to 5 times x equals to m plus n plus 5. We can say then that by the induction hypothesis, m plus n is equal to 5 times y, or yeah, 5 times y plus x. And then we can say, okay, 5 plus x is 5 times y plus 1. Which holds for some integers xy. Therefore, our inductive step holds and our proof by structural induction is complete. And we have proven that wink. I say, and since there are no other elements in S, our proof by induction complete, and we've proven that this. They might be a little bit like on the bar for that last sentence, like because there are no other elements. Because if there are, then you know we're not done yet. We would have to prove other stuff as well. But we here are done because there are no other things in our set.
Wait, so we can use the thing we want to prove as the induction hypothesis? Like, isn't that what we need to prove?
That's how we do any.
Oh.
Yeah, for the induction hypothesis is also like the thing we want to prove over here. Like.
Oh.
Yeah, we use what we want to prove that it also holds for the next one. Because we want to prove that if the induction hypothesis holds, then the inductive step holds as well. And the same way it goes in here, it also goes in here, or in here, because the set S is recursively defined.
Oh, okay.
I'm gonna put some more slashes in here so that this is a little clearer. Okay, proof 11. For any set ABC, prove that the intersection of A union, the intersection of A and B minus C is equal to A minus B, or the intersection of A minus C and B minus C. So if you open up this one again, oh, excuse me. So we want to prove that. Oh no, that's like a third one as well. Oh, that's gonna be a bunch of drawing. But you know, it's all good. That's why we're here. We're here to learn. How this is good? Yes, okay. They're not the prettiest circles. I'm gonna be honest, but you get the picture. Hey, that one looks good. So we have on the top the union of A minus B, or union.
Yeah, it's union.
Ah, yeah. The union of A minus the union of A and B minus C is equal to A minus C union B minus C. The union of A minus B. The union of A and B minus C. I was about to say that's not correct. So the union of A and B is this whole thing, and minus C is only this thing. Yeah, so we're talking about only this.
No, and everything in A that is not in C, and everything is in B that is not in C. Right?
Yeah, that's a good part. That's a good one, because I thought about not the union but the
intersection, yeah.
Yeah, excuse me. So we want to have this, and then we say that is the same as the union of A minus C and B minus C. So A minus B is this part. No, not that part. And B minus C is this part. So we can see that if we add these two together, we get the big old Mickey Mouse, all happy. So, yeah. We can see that this makes sense. So we can go on and try to prove it. But after this proof, I'm gonna call in a little break for like 15 minutes, because we've been going for like fucking 2 hours already. That's half a gig of recording right there. I hope my XSplit doesn't automatically break after 2 hours. That would be sad.
Just keep in mind you still have proof 12 to do so. Good luck with that.
Well, actually, I have a little ace on my sleeve for this one.
Yeah, probably that X, Y, and Z can be 0, right?
Yeah. It says there it has no solutions for integer disk. Yes, yeah. I'll go over that like after the break though. But yeah, we won't spend a lot of time on this one. Let's just say it like that. So we want to prove that A cup B minus c is equal to a minus c cup b minus c. So if we write that in predicate logic, we're just going to do a direct proof, no fancy shenanigans here. So if we write this in predicate logic, that means the element of x that are in A, logical OR, the elements of x that are in B, minus c is equal to this stuff. So then we have, and this is the element that are in there and not in C, right? Yeah, I think so. Is this a lowercase c? Should be capital C. Okay, so yeah, the elements of x that are in A or B and that are not in C. You can see that still makes sense with our picture, that are in A or B and not in C. Yeah. Okay, so then we can use the distributive law, because here we have an or and an and. So we can say, let's see, the distributive laws for let's say here, I've got a OneNote, by the way, with like all the rules, so that's why I'm sometimes stuttering a bit. So if we have A and B or C, that is the same as saying A and B or, yeah. So that means we can say this part and A, or this part in C. So yeah, with two closing brackets. So we have to prove that this is true, so then we convert this into, oh yeah, okay, I was already saying, hey, I did some more work than that. So here we have x part of A or x part of B and x not part of C. It that turns into x part of A and x not part of C, or x part of B and x not part of C. And then by definition of the negative sign, we can say, we can copy this thing and say that this is actually A minus C, or B minus C, and then we can say by definition of cup, and in this case will be by the definition of the union, we can say that this is equal to the cup of B minus C, which holds, and therefore we have proven that yoink paste box. Okay. Somebody mentioned that it would be a good idea to call in a break, which I 100% agree with. Let's say like 15 minutes, little toilet break, little time to chill out for a bit, and I will see you guys back at 15:30 if that's alright.
Nice.
Okay.
Yeah, nice.
Good job, guys. So far, we're more than halfway there. All right. So, for integers x, y, and z and n, prove that x to the power n plus y to the power n equals to z to the power n has no solutions for n greater than 2. This is, somebody asked me this as like a trick question, since it's supposed to be like super duper hard. But they asked it, either they asked it incorrectly or I rephrased it real quick. And here it says for integer z. So I can say x, y, z equals to 0. And in that case, 0 to the power of n, or let's say also n equals to 3, because it has to be greater than 2. Then I can say 0 to the power of 3 plus 0 to the power of 3 equals to 0 to the power of 3, which holds, which disproves this claim, or statement. Yeah, they meant to ask like another thing, which is like really hard to prove and took like 150 years to prove, but yeah, this holds for integers thing. And that's why we love for integers this and this and this. It has no solutions, because then just a counterexample is enough. So then, we have proof number 13. Define set S like this. I'm going to add a few new lines in here. One is in S. If x is in S, then x plus 3 is in S. If x divided by 2... if 2 divides x is in 2 divides x in S, then x divided 2 is in S, and nothing else. Proof if k is in S, if and only if k is divisible by 3. Okay, so we have a set here, and we can try to sketch a little image of how what this set is going to look like. So we have a set of 1, 4, and then like, yeah, that's by the base case. We have a set of 4, let's see, 4, 7, 10, 13 by the first case. And then for the second one, this is divisible by 2, so there we go, this is also divisible by 2. So this basically contains all the numbers. Is that correct what I'm about to say? No, not all the numbers except for the ones divisible by 2, but basically if a number is not... Wait, does that mean... Okay, so the reason I'm kind of stuttering here is because here they say prove that if x is in S, then left right arrow, so if and only if x is not divisible by 3. But that means that if a number is not divisible by 3, it is also in S. Let's see, if we go on, would this include, like, say 22? Oh yeah, I think it might actually. So if we go on here, this comes 16, 19, 22. So 2, 5, 8, and 11. Yeah, I see. So this is, so the first set is the set of all numbers for which 1 plus k times 3 for any k. And this is 2 plus k times 3 for any k. Or yeah, let's use like x and y. So we know by intuition that this set will contain all the numbers except for the numbers divisible by 3.
One thing.
Hmm?
Yeah, the first line after the proof 13. Define set S like this.
Yeah.
Shouldn't it be 2 is in S and not 1 is in S? Because if it's 1 in S, then the second recursive definition, then it's not true. It's basically the number 1, then the number 4, then the number 7. But if it's 2, then the second recursive definition is true, and from there we get the number 1, then we can get the number 4, and so on.
I think this one holds as well, because
if you have 1 at the start, then we cannot get the even numbers.
yeah, we can, because
yeah,
the 4 and the 10 and the these numbers will all be in
here.
here.
We can go back. Yeah, exactly.
Yeah.
Have you given a proof that if a number is divisible by 3, it is not an S? Because that's also important.
Yeah, we have to prove it both ways. I think either that, or we can prove that saying that x is not equal to 3 or is not divisible by 3 is the same thing as saying k is an S. Because like the left-right arrow is the same as saying equal sign, or like they're interchangeable. So I could say like by definition this is the same, but or not by definition. Would it be by definition? But yeah, we have to prove that. So let's see. We're gonna do this using structural induction. We will prove this using structural induction. Actually, let me keep this here as a note. we will prove this using structural induction. The base case yeah, okay, yeah. So the base case is S 1 is in S. And let me put some brackets around that. Well, 1 is 1 is not divisible by, or 3 does not divide 1. I think I'm messing up the order here. Yeah, I'm messing around the order. Sorry guys, give me a sec. We have to prove that 3 does not divide k, because otherwise, you know, k could only be like 1 and 3. I think, is the rest correct? Yeah, 2 divides x, then the half of it, yeah. Yeah. Okay. So we prove that 3 does not divide 1, which is correct because there is no integer, let's say x, for which x times 3 is 1. So we have the inductive induction hypothesis thesis number 1, which is that if x is in S, then we already did a structural induction. How did we do that there? Yeah, okay, with the induction hypothesis we used to prove that. Yeah. So we have the induction hypothesis, which is if k is in S, then k does not divide 3. Or 3 does not divide k, yeah. Which can be rewritten to k in S left right arrow 3k 3 times x is not equal to k for some integer x. Let me add some more enter signs here. Okay. The inductive step is that if if x let's see. Yeah, if x does not divide 3, then x plus 3 does not divide 3. Yeah, okay, that makes sense. Because we're saying, okay, we have the first part of this, that holds for the thing we want to prove. Okay, so then we want the second part of this to hold for what we want to prove as well. So, okay, then we can say x plus 3 let me use another number here, actually. Let's call this y. So let's say in this case x plus 3 and mid 3. And we can then say that by the induction hypothesis, we know that x is equal to so like if k is in S, then let's see how,
Just so you know, your writing is not divisible the wrong way.
yeah, yeah, my bad.
Yeah.
Good call. I keep messing those up, so like if I messed it up again, just ever tell me, because I don't want you guys to like take over something that's wrong. Okay, and then for this way we can say n mid means that 3 wait yeah, okay, 3 times z equals to x plus 3 for some integer z. This should be not equal. I'm really struggling because there's a lot of not equal here, and that's I don't like not equalness. Is there a better way to say this? That like
you can technically write that x plus 3 must be 3 times some k plus some c, where c is not equal to 3. So then you will have an equality sign, but with some additional variable, you could say. But then if you subtract 3 from that variable, well then since c is not divisible by 3, then minus 3 will still not be divisible by 3. And that pretty much proves this.
Yeah, true. Okay. Okay, so we can say that which can be rewritten to this, which can be rewritten to is equal, or k is equal to 3 times y plus c for some integer y, where c in the set of 1 or 2. I'm not sure if this is clearer than just splitting it up into cases. Or, yeah, the set of. So I'd have to do it like this. Okay. I'll see how far we can get with this, and otherwise I'll just split it up into cases. Okay. So then we can say this. Okay, and then we can say since x is part of k, or S, we can use the induction hypothesis. And then we can say that 3 times z is not equal to, and then this would be 3 times y plus c for some integer y where c in 1 or 2.
Sorry for the interruption, but when I say 3 times z does not equal x plus 3,
Yeah.
it's line 238. It's for all integer z.
Yeah. I see. And oh wait, this is for some integer y for all integer z.
Yep, I guess.
Yeah. Oh, all these inequalities. Okay. In this case, we can say this tree is 3 times 1, and this is y plus 1 plus c, which holds because the left side is always a multiple of 3 and the right side will never be a multiple of 3. Okay, it's scuffed, but I think that's actually it for this part, because we actually have 2 inductive steps. So let me write that out real quick with proper enters. 3 times z is not x plus 3 for integer z. Since x part is h, we can use the induction hypothesis. I need to put an enter here. 3 times 3 times z is not equal to 3 times y plus c plus 3 for some integer y where c is 1 or 2. And then we can say 3 times z is equal to 3 times y plus 1 for some integer y. Yeah, because the left side is always multiple 3 and the right side would never be multiple 3. Okay.
Also, wait. Also, there is this line when you say inductive step, and then you have x divides 3 instead of 3 not divides x. So it's, yeah.
Yeah, I messed that up a lot. Thank you for correcting me. Okay. Yeah, you also use divide on the right side. I think that's it. Yeah. Okay. So here I'll say inductive step 1, and then I'll add here inductive step 2. And here we can say that let's see. So this is what we want to have. So if I put this down here, let's see, recompile. So in this case it will be 3 doesn't divide x. Yeah, okay. So in this case it will be. Oh wait, why is there a 2 here? Oh yeah, okay. I'm confusing myself a bit. Sorry that I'm talking to myself, but here we have 3 does not divide okay, I'm trying to look if I can get something out of my brain that makes sense.
I think that you can write if 3 doesn't divide x and 2 divides x, then 3 doesn't divide x divided by 2.
Ah, yeah. Okay, if 3 doesn't divide x and 2 divides x, I'll add some brackets to add a little bit of clarity there. Then 3 does divide I'll add one more pair of brackets. Okay. So we know that or that x equals to 2 times z for some integer z, or I'll use I'll use a here, and x, and then I'll copy this part again. Wait, do we even... Yeah. Okay, so we know that x equals 2 to a for the integer a, and x is equal to, and then I can copy the part here. This part. X equals to 3y plus c for some integer c where c in that set. So we know that x to a and x is 3 times y plus c for some integer c where... Okay. So... Okay, I'm gonna start off by taking the second part again, and proving that this is true for the first part. So we have 3 does not divide x times 2, but we know that x is 2 times a for some integer a. Oh, that's another enter too much. Oh. So we can say, instead of x times 2, we can say 2 times a for some integer a. Then we can take away this fraction and we can say this is a for some integer a. And wait, oh, wait. We know that x doesn't just divide a, it's also part of the set. So we won't use x here, we'll use another thing. So let's say y. No, we already used y. I'm running out of letters. Let's use, we already have c, let's use d. So we have we have d, which is 2 times x for a number x that is in the set. So for some integer x that is part of S. Yeah. And we have that d is 2 times x for some integer x in S. Okay, so then we have this, and from our induction hypothesis, we know that x is equals to 3 times y for some 3 times y plus c for some integer whatever, blah blah blah. And because we know that that's equal to x, we can say 3 and mid this thing the right side is 3 and the left, I'm literally dumb. Left side is 3 and the right side will never be 3. I don't think we can make a statement here yet. Oh no, because it's still in the form of n mid. So that means
I
we...
just want to say, I am so sorry for this.
No, but this is good. This is good. We will learn the notation.
I didn't really expect it to explode like this. God.
Yeah, but the only reason why this is so...
He shouldn't have included if and only if, because now we have to prove the other thing as well.
Yeah.
Oh yeah,
Also,
you are making
also on
a
the
good
second
point.
line in-
That means that we just take this and we remove the if and only if part, because I, honest to God, cannot be asked.
Yeah.
Yeah.
Let's
So
prove it only the one way. Also, on the second line in inductive step 2,
the inductive step 2, second line.
it should be either 2 times x equal to 3 times y plus c, or d equals to 3 times x. 3 times y plus c.
Wait, what did you say?
And it shouldn't be x equals to 3 times y plus c. It should be either 2 times x or d, because you
Oh
just
yeah.
Yes.
Yeah,
Since
makes
you
sense.
already deleted the if and only if part, can I just give you a hint about how if the number is divisible by 3, you can say that it is not an S?
Yeah.
So you can get to a number divisible by 3 in 2 ways. You can do x plus 3 is that number, or x divided by 2 is that number. So to get to that number, you have to, let's say the number divisible by 3, let's call that x. So if you...
Okay, wait. Let me finish this proof, and then we'll get to that, because otherwise we're going to confuse x's.
Okay, of course.
Yeah. Where, let's see, so then we can say d is equal to that. Actually, no, because we're talking about the x, which is not divisible, and the d, which is equal to 2 times x. So everything...
you changed it, so now it should be 3. D is not divisible by 3, and D is divisible by 2. And we should prove that 3 does not divide D over 2.
I don't think so. Because we're talking about the number x, which
you changed the letter, that's why.
Yeah, but here I have the integer x that is part of s. Like, all of this is still correct. We're talking about x, which is part of s, which is not divisible by 3, x that is divisible by 2, then the only reason I'm introducing d is because it makes it easier. That does mean that this is...
Yeah, exactly. It should be D at the start of the inductive step. Because otherwise you say that D equals to 2 times x for some integer x that is in S, and then the next thing you say is that x is not divisible by 3. Because we have a remainder of 1 or 2.
Yeah. But the issue is we're talking about x that is part of s.
Yeah.
And
no,
this is still correct, because this is all still in form of x. So this is not correct.
No, I think it's the other way. We have D in x, D in x. We have D in C, and we should prove that x is in C as well. Because we have, if 2 divides x, then x over 2 is in C as well.
Yeah. D equals 2 times x.
Yeah. Not for some integer x that is part of S, but for some integer D that is part of S.
Yeah.
And we should prove that x is part of S.
Yeah. Oh god, why are there so many numbers and letters and... Okay. It's okay, I choose to do this. So we know that... But in that case, wouldn't it be just nicer to say x equals to 2 times d? and yeah. So we can say x then here. We can say 2 times d in here. See x in with d. But what do we know about d then? We know that
We don't know anything yet, but we should prove that d is not divisible by 3. Actually, no, I think we know that d is in C, but we should prove that it's not divisible by 3 or something like that.
okay, so if we know that for some integer d in S. Oh yeah, because okay. Yeah. So then we can say because the in induction hypothesis, because d is in S, we can replace d by this. Yeah, okay, now we're good again. And then we can say d or 3 times y or times t, whatever, for some for all integers t by definition of n mid. Okay. And this holds because the left side will always be a multiple of 3 and the right side will never be a multiple of 3. Enter, therefore we have proven that the base case isn't divisible by 3 and all the other elements in the can I not spell? Divisible. And all the other elements in the set added by the recursive definition aren't either. There are no other elements in the set and therefore our proof by structural induction is complete. Box. And we have proven. Remove this. Yoink this. Okay. Okay, that makes sense. Proof 14. Ah, here we go. Here we have.
Wait, can you hear first the other way of proving?
Oh yeah. Somebody said he knew the other way around. So let us hear.
Hopefully he isn't the one who left recently.
Oh, fair. No, in that case, we'll go on proof 14.
Yeah.
So proof 14, we have a set of letters. Let's see. And then I'll add one more. There are no other elements in S. Prove that the number of A is odd in every string. Okay. Again, we will prove this using using structural. We will prove this using structural induction. Also, I should probably say for any x in S, take for any x in S, take. Oh, for any. Okay, I think that's correct. So now I go on. Base case A in S, the number of A in A is 1, which is odd, and therefore the base case holds. Inductive
I think you just changed the second one.
Hmm?
Inductive step 2 in the previous one.
This one?
By changing X to D.
Um,
Can you scroll up in the PDF?
So, in the PDF.
Yeah.
So this
You're
should...
saying that 3D is not... Oh, okay.
Yeah, I'll change that. So, but it
Yeah,
should
it
be
doesn't
for...
matter that we have an X in step 1 and an X in step 2, I think.
Okay. We take those. Okay, so we have inductive hypothesis. I'll add hypothesis. So we have if oh yeah, okay, so that's what we want to prove. So
we can do it like Stefan and have a function that
yeah,
counts the number of ways in
smart.
string. Yeah.
To aid us in our proof, we will define a function f of x, which returns the number of a in x. Function. Base case. And in this case we can say f of a is 1, which is odd, and therefore the base case holds. So we can say if x is in S, right arrow, f of a times k. Let's use this division first, and let's 2, and then we can say that this is same as saying that's the other way around. 2 and mid f of a. That 2 times k plus 1 is equal to f of a for some integer
f of x.
Okay. Yeah. Okay.
Oh, I mean f of x, not f of a.
Oh yeah, good call.
Yeah.
Okay, so now we will go on and say that for our inductive step 1, let me scroll down a bit. We have that if x f of x equals to 2 times k plus 1, right arrow, f of xb equals to 2 times let's say m plus 1. We can do this by saying we take this part and 2 times f of b is equal to f of x plus f of b, which is equal to f of x plus 0, since x is part of S, f of x is odd, or in this case, we can use the induction hypothesis. F of x plus 0 that is equal to let me actually split this up in a few lines because we want to prove that this is equal to this.
In my opinion, we don't need to introduce M.
Mhm.
And just like, I don't think we need to introduce M on this line. Yes, we can just like start working on f of x and b, or whatever we call that thing.
Yeah.
But yeah, I mean it doesn't matter.
Yeah. I'll see if I'll change that. Which in this case we can use the inductor hypothesis, which means that 2 times k plus 1 plus 0, and for consistency's sake I'm gonna split this up into 3 parts and say at each line that this is equal to for some integer m equal to this, equal to this, and I'll add enters here, equal to 2m plus 1. And then we can take this one away, and we can say since k and m are both some integer, this holds. Another enter, inductive step 2, yoink this. We have 2 other steps, so if inductive step 2, that means that a, b, x, a, yep. So then we can take the second part, and we can say this is the same as saying f of a plus f of b plus f of x plus f of a. And then we can say that f of a is 1, f of b is 0, and f of a is 1. We can rewrite that to two plus f of x. Since x is part of S, we can use the induction hypothesis, and then we have f of x, or no, this one, and then we change f of x to 2 times k plus 1. And then we say 2 times k plus 1 plus 1, and then we can say since k plus 1 and m are both some integer, this holds. And then we have inductive step 3. Boy oh boy. If f of x is equal to that, logical and f of y is equal to 2. Let's say, let's add another one here. So we have k1 and k2. Then f of xya equals to 2n plus some integer m. Okay, so we'll take this. We will say that this is equal to f of x plus f of y plus f of a. We can say that this is equal to this, and then we can say that by because x and y are both in S, we can use the induction hypothesis. We can call this 2 times k1 plus 1 plus 2 times k2 plus 1 plus 1. And then we can say this is 2 times k, so this is plus 2, and this is plus 1 in the end. Okay, so we can say this is 2 times k1 plus k2 plus 1 plus 1. And then we can say, and since k1 plus k2 plus 1 is an integer, this holds. And I think that were all the inductive steps. Since oh wait, let me add another step here. Since k1 and k2 are let's say k1, k2 and 1 are all integers, this thing is an integer and this holds. So this is like the same as saying m is equal, or not m, h is equal to k1 plus k2 plus 1, since m is an integer, whatever. I'm just taking out the middleman here, but it should still be understandable. So now we can say, since there are no other elements in S, we have finished everything we needed for our proof by structural induction, and we have proven that. Scroll up, scroll up, scroll up. There are an odd number of A in every element in S. Proof 15. Oh god, I can't wait to do the last few. These are not that hard. Okay, let A be the set of all bit strings of form O to the power 0 to the power of n, 1 to the power n, with n in all the natural numbers. Let B be the recursively defined set. 0, 1 in B. If W is in B, then 0, 1 is in B, and there are no other elements in B. There are no other elements in B. Now this might be something. Okay, so if we go here, let A be the set of all the bit strings form. We're going to set as 0, 1 is in B, and W, if W is in B, then 0, W1 is in B. There are no other elements in B. Prove that A is equal to B. So that is basically stating that all the bit strings are of this form. To prove this, it will suffice to say that all the elements in B are of the form. Okay, so what we're trying to prove is that every element of B is in that form. So we have the base case. We will use structural induction. Base case 0, 1 in B. 0, 0, 1 is of the form namely with n is equal to 0 or 1. And by the way, if you guys don't follow, this is like the I guess Pythonic way, where like the string O to the power 3 is equals to 000. So yeah, namely n is 1. induction hypothesis if let's say W in B, then wait, the induction hypothesis is that what we want to prove? So that means that if we have W in B, right arrow I need a quicker way to say this. We will use a we will create a function of form x which takes a bit string x and this is not a function, this is a predicate, right? And return true if x is of the form and false otherwise. We will use structural induction. Then of form W. Oh. Okay, and then we say that if inductive case. Yeah, okay, so this is the inductive case. We'll add a few enters here. Okay, so the inductive case is that if of form W, then of form 0 W1. Since W is of form, it can rest as like that, and 0. Therefore, we can express 0 W1 as 0 tab 1, or, and in this case it would just be m plus 1, which is still off form. Because we're just adding a 0 in the front and 1 to the end, which is that is still of the form. Therefore, this holds. There are no other cases where there are no other elements in B, and therefore we are our proof by structural induction is done. However, we have proof A equal to B. Yeah, no, okay, we have disconstructed A into the function of form because all elements of this form are in A. Yeah, okay, so that should be good. Structural induction is done. Therefore, we have proven that A equals to B. or we have proven that all elements in B are of the form which is also the set of A, therefore A equals to B. Box. Okay, this one should be a lot easier. Like a lot. I think we actually only have easy proofs left to go, so that's really good. Okay, so here we have for all n in natural numbers, if 3 divides 5 to the power of 2n minus, or 3 divides, yeah, okay. So we will prove this with induction, with proof by induction. The base case n is equals to 0, 3 mid 5 to the power of 0 minus 1 equals to 3 mid 0, which holds. Induction hypothesis if no if, so like say we induction hypothesis is this, which can be rewritten as this. So we can say 3 times x equals to that for some integer x. Inductive step. I swear to God, I can dream these things by now. Yeah. So we can see 3 mid this thing, right arrow, 3 mid this thing. So
don't forget it's 2n plus 2 or 2n plus 1 in parentheses.
Where?
It's 2n in the inductive step. What you just wrote.
Yeah, 2n plus 1.
2n, yeah, but it's 2n plus 2 or 2 and then between parentheses n plus 1.
Huh?
I see you're getting a little tired, but the inductive step, you increment n by 1.
Yeah.
Now you're incrementing 2n by
1. Yeah. God damn it. Brackets matter, people. God damn it. Yeah, no, it's like I'm 3 hours in.
Yeah, actually.
Yeah, thank you for keeping me sharp, for real, man. I don't want to like put the wrong information out there. Okay, so we have this, which is then in turn equal to saying that 3. No, let me make another line for that. I knew it would happen. That's why I put like the easiest things for last. 3 times y is equal to that for some integer y. Then we can say that this is 2n plus 2 minus 1. And then we can split off this 2n, saying that this is times 25. Yeah, that's still correct. And let's see. Now I want to say I want this to be in the form 5 to the power 2n minus 1. So I'm just going to say minus 1 plus 1. and I can replace this with 3 times x, and then we can say by the induction hypothesis, this is equal to that, and then we can say this is equal to 3 times 25x plus 25 minus 1. This is equal to that time plus 24. 24 is equal to 3 times 25x plus. Okay. And then we can say since x is an integer, 25x plus 8 is an integer, and y is also an integer, is some integer, this holds.
Nice.
Yeah.
You're getting there. 19 proofs in 4 hours.
Yeah, I mean, we're currently at like 2 hours and a 15-minute break and then 1 hour, so we're only at 3 hours.
Oh yeah.
Yeah, we're really getting there.
Hey, dude, I remember you once said that you were afraid you were going to struggle with RNL.
Yeah, like, honest to God, the reason I'm doing this, like, I'm not afraid of struggling with RNL. I've got like a 9 for my midterm, but like, I wanted to train proofs and not just do 1 or 2. I wanted to go all the way, but not only did I want to do that, I want everyone to be able to look at how it went and see the mistakes I make and learn from them. And that's why I decided to do this, and it's a really, really bad idea, but in the end it's probably going to be worth it or something.
You probably won't have to study for the interim at all at this point.
Maybe a little, this is only proofs, and there's still going to be like some stuff with onto and injective surjective, but for the most part, no. This concludes our proof by induction, and therefore we have proven that. I wish all the other proofs were like this.
You mean 20 lines long?
Yeah. Box. Yeah, no, let me add another, let me add another, yeah.
Virus programs, Mike is having a bit of a virus.
Oh, sorry.
Okay, so only 4 to go. So we have x intersection B is a subset of A is a subset of X or A union B for any sets A and B. Okay, so first step is going to be writing this into the other, into like propositional logic. So we will say that x in A cap x in B is a subset of x in A is a subset of x in A x in B, and let's see, cap is the and sign, so this is a logistical and this is a logistical or. Is that correct? And let me add some brackets to make this a bit more legible. Respect for you guys, by the way, for sticking with me all the way. And for the people on YouTube, if you're here, I have respect for you as well. Okay.
3.5 hours long video.
Yeah. I'm not even sure if I can upload this. I might have to do a part 1, part 2 thing on YouTube. Okay. So...
Just 10 hours of raw footage.
There are like 10-hour videos, so it shouldn't be a problem.
Yeah, that's true. Okay. So, we have this. But we know that being a subset of means that everything that is in the first one is also in the second one. Yeah, yeah, okay.
So so you can make like an implication. For every x, if x is in A and in B, then x is in A.
Yeah, I think this might also be like. Yeah, okay. Let's turn this into two separate problems real quick, because I don't like this tree subset sign. So I will say this is a problem, and and x in A is a subset of. Oh, forgot a backslash. Is there like a proper definition of something being a subset? Oh yeah. I have this thing right here, and it says is a subset of A is a subset of B for every x part of A. If x part of A, then x part of B. Then we will use that.
Can you share that picture?
Mm-hmm. What did you say?
Can you share that picture on your shortboard channel?
I'm not sure if I can, because these are the notes I'm going to be using for the RNL exam, but it's literally a screenshot of the book.
Oh wait, it's from the book. I see.
Yeah. This is just like everything in this thing is a screenshot from the book, but I'm not really allowed to like share and distribute them, because then I'm not allowed to use them again, and now I have to make new screenshots.
I see. Alright, never mind then.
Okay. Yeah. Okay, so let's call this equation equation 1, and we'll call this equation 2. And or equation 2. To prove the original statement, we have to prove both equation 1 and equation 2. Okay, recompile. Okay, so we'll start out with the first one. That's this one. We'll start out with equation 1. That's this one. So x in A and x in B is a subset of x in A. And with the definition of subset, that means for every x, if x is a part of the first thing, then x part of the second thing. So we can just replace this with right arrow. So then we can replace this with a negation of the first thing or the second thing. Lor the second thing, x in A. Oh, I'm forgetting my slashes. Should always be consistent with your slashes. The negation of x in A and x in B, that's x not in A, or x not in B. Oh. And because this is these are all ors, we can take away the brackets, and we can reorder this. So I can put this lor near the end, and lor stands for logical or, by the way. I'm gonna put around some more brackets around like the ins to make it a little bit more legible. Oh yeah, okay. And this has to this has to hold for all x. And because we know that this part, so x is not in A or x is in A, that means that's the universe lor x not in B, with u being the universe.
Sorry, but I think because you're talking about logical operators here and not set theory, you don't need to use u, you need to use t or true or something.
Yeah. Yeah, okay, that's fair. That's a very good point. And therefore we have d by the, and then I'm gonna scroll up in my fancy book, the identity laws, which is true, and therefore equation 1 holds. Now on to equation 2. For all x should hold. And then we'll take the second one. Okay, therefore we can say this is a subset of is equal to right arrow. And then we can copy this. We can say instead of right arrow we can do a logical OR. And we can change this from x in A to x not in A. And we can change the brackets around here a bit as well. And then again we will have x not in A or x in A, which is true. Lor B, and then by identity law, this is true. True by identity law. Therefore equation 2 holds as well. Therefore we have proven that. I'm gonna add a little extra step here, which is I'm gonna take this not sign around and out the back. I'm gonna say turn this back into the negation here. So here we will have oh yeah, I keep forgetting my backslashes. Okay, so here in the end we will have not something or something, which is true. Because like it's a little bit too big of a step to say A is not in B or A is in B, or X is not in A or X is in A. So I'm gonna put that step in here as well. Because in this case we're using X in A like it would be a predicate. Okay, so this holds. Nice little box there, sick. Okay, this is like, okay, 3 more to go. And this is from the helpful homework as well, so you guys should all have already done this. But I'm gonna assume there's at least some people who haven't done this yet. Okay, so we're gonna do, we will do a proof by induction. You can tell I'm doing one proof more than the rest. Base case, and this is for all n, for all natural numbers n, and I don't know if that's natural number bigger than or equal to 1 or not. Okay, so base case, we'll see. From I is 1 to, oh yeah, I is 1 to 0 doesn't make much sense. And bigger than or equal to 1. Can I use greater? Yeah, greater than or equal to. And then with an n before it. Okay, so we can say here that base case n is 1. And then the sum of this whole thing from 1 to 1 of 1 squared is equal to 1 cubed. Which is the same as saying 1 cubed is equal to 1 squared. Right, left arrow, 1 is 1, which holds. Oh. Right, left arrow, left, right arrow. Okay. So our base case holds. New line, inductive hypothesis. And that's just this thing. Or this thing. Inductive step. And that is n plus 1 is equal to this thing n plus 1. Okay, I will then proceed to doing this and paste it a few times. Okay, so again we will do the thing where we say we take out the plus n plus 1 thing here, and we will take out the plus n plus 1 to the power of 3 thing here. And you can see that there's a difference between where we take it out, because here this whole thing is squared, so I have to add n plus 1 to this whole thing inside of the brackets, and here it's just I cubed, so we have to cube this. I think it's the easiest way to do is just take this one out and substitute it in for that one, because we just have that one already. So I'm just gonna do that and copy this one and say, because this part is equal to this part, I can just copy this over and do yoink. Recompile. Yeah, okay, this seems easy. So then I copy this one over and I say plus n plus 1 squared is equal to which one of these will be easiest to prove? It might have been smarter to do it the other way around. But at the same time, then I'm just going to have some of the sums of I. I'll see how far we come. So I can group these two together. Because these should, in theory, be equal. So let's see how far we can get. So we have this whole thing squared plus this whole thing squared plus 2 times this thing times this thing. And that middle term is kind of what I'm worrying about, because I'm not sure if there's like a neat little way to get rid of this term. Oh, and yeah, I should just grab this as a one term. Or actually, this thing is not squared. Yeah, so this is the left-hand side, which we get from this thing squared plus 2 times this thing plus 2 times this thing times that thing plus that thing squared. Okay. Okay. Interesting. I see we on both sides we can subtract this this whole contraption. Like this isn't the easiest way of doing it, but we should get there in the end. So now we have that. Let's see, is this still correct? We subtracted that thing, we subtracted that thing, so yeah, this should still be correct. Okay, yeah, but now we have this thing that's like really annoying.
Yeah, you gotta use the n times n plus 1 over 2 thing.
Yeah.
The sum of sequence.
Yeah. Let's actually pull that one up. So we have the sum is God. Is there what would that be called? Sum of all integers.
You should look at the induction proof. It was like an exercise after the induction topic.
Okay, so the first mention of that's mathematical induction.
Yeah, it's like after this one. So exercises like.
Yeah.
Okay.
Wait, can you hear me? I did this one earlier and I used a different method. There's the formula to do the summation, like arithmetic sum of an arithmetic progression formula. Yeah, that shot.
Yeah.
Yeah, exactly.
So we can use this one. So we can say.
Also, I just joined, but another friendly reminder that you shouldn't like scratch things from like left hand side and right hand side. Because you should prove that they're correct and not assume that they are.
I mean, honestly, we have to prove that this is true.
Yeah.
So if we just like mess up the left hand side, as long as we still prove the same thing, it should be correct, right?
Yeah, but you should actually have like the question mark above the equal sign, and you shouldn't like touch at the same time. So, for example, you cannot like, yeah.
I don't know, because I think like when you have.
In my opinion, I mean it's easier to do like only the left hand side till you get the right hand side. Yeah.
Yeah, true, but like. If we say that this is equal anyways, why wouldn't we be able to change the right-hand side?
This is.
I mean, yeah, it's just like the point of induction is proving it. So I guess you would say like show this, and then you just work on the left-hand side. Is what he means.
Yeah.
Which I also do. So.
So you work only on the left-hand side, and you use like the induction hypothesis.
I guess you can do it your way as well. It doesn't really matter.
Yeah, I think my way is legal too. Yeah, I don't know.
Unless something you're trying to prove, it's not actually correct.
Yeah, so but then you're not gonna end up proving it anyways because it's not true. But yeah, I think like, yeah, being able to do this just makes this one a lot easier as well because if they're gonna be equal anyways, then yeah, I think this is legal.
Also, if you want to work with both, you can make them like. The left hand side minus the right hand side equals 0. This way you can work with both.
But that's the same thing as just. Then I'm already modifying the right hand side by subtracting the right hand side.
Yeah, that's why. Yeah, it's up to. I mean, it's up to you. If Stefan approves both, then yeah.
Yeah, I think he does. I might send him an email later today, but I might forget. But yeah, we have found out that this is now equal to the fraction of n times n plus 1 over 2. Recompile, see if that's correct. Yeah, we already have a 2 here as well, so we can take out this 2 and take out this entire fraction. Yeah, and now it just seems like I'm just gonna do some work. N squared plus n times n plus 1 plus n plus 1 squared is equal to so let's see, we have n cubed plus
you don't need to do that.
N squared, probably not.
No, online, let's see, line 392 from the latex, you can just group like n plus 1 with the other n plus 1. So you get n plus 1 squared times n plus 1 plus n plus 1 squared, so it's n plus 1 to the third.
Okay, so yeah, you make a good point. So if I say n plus 1 times n times n plus 1 plus n plus 1.
It's even
That-
even now it's a bit more complicated, but yeah.
Yeah, but like I only have to work with quadratic now instead of cubic, which is a lot nicer. So now we have n squared.
No, you don't need to do that. You just group them again.
But you can't go from n times n plus 1 plus n plus 1 to
No,
n
you
cubed,
can,
right?
you can group them again, so you get n plus 1 times n plus
Oh,
1 times n
holy
plus 1.
shit! I didn't even see that. That's so sick. So we have
N plus
m
1. Yeah.
n plus 1 times n plus 1. Ah, that's sick. Ah, that's hot. Okay, and that's just the same as saying, yeah, which holds. And then over here we can say for any arbitrary integer, or for any arbitrary integer n, n in capital N, this stuff holds. Which concludes our proof by induction, and because we chose an arbitrary integer n, this proves that for all natural numbers n, this thing, or for all natural numbers n greater than yeah. Well, I guess I should say for an arbitrary integer n greater or equal to 1 in capital N, because those are the restrictions we have put upon our integer, and the same here then. Okay. Box. Okay. Proof 19. X is odd if and only if the absolute value of x is odd. Seems a lot easier. So we want to prove that to prove x x equals to 2y plus 1 right arrow. There is no real good way to do the absolute value in LaTeX, I don't think. Or actually, let me see. Abs LaTeX. Yeah, then I need to import a package, and I really CBA. So I'll just use the mid things. So then we say, and this should be a right left arrow. Mid equals to 2 c plus 1. Left right arrow. Okay, so we can split this up into two proofs, different things. Namely, oh, and I should put here for some integers x, y, z. Or this is actually x, y, z for any integer x. Split it up into two proofs. One which is this thing. Oh, right arrow this thing, and proof number 2, which is right arrow, but then the other way around. This is a good one because we have like so far we've been just missing all the if and only ifs. And then this is for some integers xy for all integers x.
Wouldn't it be faster if you test for all x below 0 and all x positive? Use those two cases. Use the case that x is below 0 and use the case that x is 0 or above. Instead of odd or even. Since with positive you can just say it's already positive, so the absolute value does nothing to it, so it's still off.
Yeah, okay, that's true. Let's actually do that then, because we didn't split any into cases yet. So we can still split it up into two proofs, namely the case where x is positive is 0 or positive, and the case where x is negative. In the case where x is 0 or positive, x is equal to the absolute value of x, which makes sense. And so if we fill that into the thing we want to prove, we get x is odd, left, right arrow, x is odd, which is correct. Which holds. Oh yeah, but now we have the ugly is odd, so I'll just put down the equals to 2y plus 1, and this is again the equals to 2z plus 1, which holds for some integer x, yz. Then we have the case...
You're using 2y plus 1 for the second one too.
What do you mean?
Since x is the same at the left and the right, you should be using y instead of z.
Yeah, true. But I'm copying this one, where we already started using z. But it doesn't really matter because they're for some y and z, and y and z can be the same, which is, you know, the case. So I could say indeed like that there will be a y, but I don't have to. Where x is a negative number. And in that case, we can fill in mid x mid equals to negative x. So if I don't, yeah, okay, I can remove this. And because we're using left right arrow, that's the same thing as saying yeah, just an equal sign, or this is the same thing as. That means we can get this, or negative x equals to 2z plus 1. And if we add... Wait, but this is not true.
You should be negating that 2z plus 1.
Yeah.
Why should you do that? Sorry?
Wait. No,
I don't understand.
X equals 2z plus 1, so minus x equals minus 2z plus 1.
Yeah, but the negation of z, or the absolute value of x, should equal 2z plus 1.
Yeah, otherwise you just do the same thing twice.
Yeah. So I don't think we should negate this. Yeah, so in this case, I think it would still be better to
You
like
should
divide it
negate
up.
x is 2y plus 1 and not the absolute value.
Hmm?
You're putting a negation over the absolute x and not the other x. The
Yeah,
absolute x is
but
equal
that's
to-
true because the absolute value of x is equal to negative x in the case of a negative number. Wait, let me see if this is up to date. Yeah, we can fill in that the absolute value of x is equal to negative x for a negative number x. So in that case, we can fill in here that the absolute value of x is equal to negative x, but the rest should still stay the same. Okay, but then we can let's see. Yeah, we can just split this up into cases. Why not? Because the left-right arrow isn't fun to work with. Can split this up into two cases, into two equations, namely equation 1. And then the equation 1 will be where we assume the first thing is true and prove the second thing is true, and the other way around for the second equation. Equation 2 where we say this is here and this is there. Okay. For equation 1, we assume x, and then this is all math, so we put it into the math brackets, and we can say filling this into the second part of the equation gives. I put a thing too quickly here. Now you can get negative 2y plus 1 is equal to 2z plus 1. Yeah, okay, that makes sense. So then we can go ahead and distribute the minus out of the brackets. So we can say negative 2y minus 1 is equal to that plus 1. Then we can add 1 on both sides. Yep, and we can get a 2 out of here, say negative y, get a 2 out of here, say this is z plus 1, and then we can say since y and z are both integers, negative y and z plus 1 are both integers as well, and since we said that this should hold for some yz, this holds. For equation 2, we assume this, which is the same as saying x is equals to negative z minus 1, because we multiply everything by minus 1. Filling that into the second. Okay, into the second part gives. My recording still running? Yep. And I'll put an enter here real quick, and then we can say to negative 2z minus 1 is equal to 2y plus 1. And then we can go ahead and add 1 on both sides, just like we did before. Get a 2 out of brackets. Wow, this proof sure is looking a lot like the other one. And then we get y plus 1, or y plus 1 times 2. And then I can literally copy this. And then instead of this I'll say z and y. This holds. Therefore, we have proven both sides of or both cases for is this, yeah, okay, for that, which is what we wanted to prove. Box. Actually, before this, both case, somebody's ear raping, please stop. For this and this, for both cases where x is less than 0, greater or equal than 0. So for all x, which is what we wanted to prove. So we basically split this up into like 3 cases. Okay. The last one, salvation, guys. Suppose x and y have opposite parity, x, y should be even. And then of course with x, y in natural numbers, or it could also be in all integers.
You're almost there.
Yeah, and this last one is really, really easy. So do you guys know what opposite parity means?
Yeah.
Yeah.
Sick. So we can say since either x is even or y is even, by symmetry, it is enough to prove that it holds for x is even. Therefore, we can write x as we can write x equals to 2n for some integer n. Therefore, x times y is equal to 2 times n times y is equal to 2 times n times y. And since n y is any integer and n is some integer, this is even divisible by 2, which is what we wanted to prove. Box. 437 lines. 2 hours and what is it? 3 hours and 45 minutes or 2 hours and 45 minutes? 3 and 45. Yeah.
Yeah. I mean, now you know.
Yeah.
Now you know it. Now you know proofs.
Yeah. If you're still watching this on YouTube, you know proofs as well. For the people in the stream, thank you so much for coming along, for staying with me this entire journey. It's been a wild ride.
Thank you for leading the journey. Jesus.
Yeah, it's been a lot of fun, but oh, it's a lot of work. I will upload both of these, like the left and the right side, to both my what's it called? To both my chalkboard channel and somewhere on YouTube, along with the video. And I'm going to end the recording here. So like, subscribe, hit that bell. No, fuck off. And I'll probably see you guys later in a bit. Alright.